Alright, so this is our Honors Chemistry lesson video for section 8.4, and it is part 3 of 5. So in this section we've been talking about intermolecular forces, and so we talked about London dispersion forces, dipole-dipole attractions, ion dipole attractions, and hydrogen bonding. And so we're just going to continue with that topic for now. So it says the dipole moment of CH3Cn is 3.9 debye, and for CH3I it's 1.62 debye. Which of these substances has the greater dipole-dipole attractions among its molecules? So when you're looking at two different molecules and comparing the intermolecular forces, there are two main things you want to look at. The difference in polarity, that kind of will give you a hint of dipole-dipole attractions or not. If you're looking at only London dispersion, you're going to look mainly at the molar mass, or like the length of the chain of the molecule. And then, of course, when you're looking for hydrogen bonding, you're looking for hydrogen bonded to an incredibly electronegative element such as N, O, or F. So it says, which of these substances has the greater dipole-dipole attractions? So in that case, normally I would focus on polarity, but I don't even have to. They gave me the dipole values, 3.9 debye and 1.62 debye. So I don't even have to look at polarity. I can easily just tell it's CH3Cn based on the actual dipole moment. Dipole moment obviously tells us the dipole-dipole attractions. Then it says, which of these substances has the greater London dispersion attractions? Well, first of all, a C and an I is much less polar than a C and an N. The molecules are of similar volume though, or shape. So what I would need to focus on for this one is the molar mass. So because I has a much higher molar mass than anything in this molecule, I know that CH3I would have the larger molar mass. And so, of course, for molar mass, we just look at the masses on the periodic table and add it up for each element. So 1C plus 3 H's plus 1I. So a lot of times you have to end up looking at molar mass when you're comparing London dispersion forces. All right, so our next one, it says, the boiling point of CH3Cn and CH3I are 354.8 Kelvin and 315.6 Kelvin respectively. Which substance has the overall greater attractive forces? Well, again, think about what boiling point is. When you boil something, you're taking a liquid where the particles are super close together and you are forcing them to spread out as a gas. So you are trying to break the intermolecular attractions. So the higher the boiling point, the harder it is to break the attractions, which means the stronger the attractions. So since CH3Cn has the higher boiling point, I know it has the overall greater intermolecular forces. Because intermolecular forces are additive too. So I already know it has more dipole-dipole and it has London dispersion. This one still has a little bit of dipole-dipole, but it has London dispersion. Since they're additive, sometimes it might be a little hard to tell, okay, well then who has more? But I can always tell based on boiling point or melting point. Alright, for the next one, maybe pause the video and go ahead and try this one on your own. I'll assume you've done that. So it says, of Br2, HCl, HBr, and N2, which is likely to have the largest intermolecular dispersion forces? Alright, so our first one, we're looking for London dispersion. So remember, all molecules experience London dispersion, but for nonpolar, that's the only one they experience. So if we look, all of these are diatomic molecules, so they would all have a similar molecular shape. Now, of course, the polarity is going to differ, but for intermolecular, or for London dispersion forces, we are going to focus on the molar mass. So if I look, Br2 is going to have the highest molar mass. So if you just look at the periodic table, Br is about 80, so 80 times 2 is 160. H and Cl is about 36 when you add that together. H and Br is about 81 when you add that together. And then N2 ends up being about 28. So since Br2 has the highest molar mass, that is the one with the greatest London dispersion forces. Now, just because it has the greatest London dispersion forces, remember they're additive. It doesn't mean it has the greatest overall forces, because Br2 is nonpolar, so it's not going to experience dipole-dipole attractions, which are stronger in general than London dispersion. Alright, so it says, which has the greatest dipole-dipole attractive forces? Well, dipole-dipole, you have to have polarity. Well, Br2 and N2, they are nonpolar. They're the same atom attached to one another, so they can't have a different electronegativity. So really I'm just focusing on HCl and HBr. When we're talking about dipole attractions, polarity is the most important. It trumps molar mass or anything like that. So HCl and HBr. If you look at an electronegativity chart, HCl is greater in its polarity difference because Cl is more electronegative than Br. So we'll just put greater polarity. So there's a couple of things that you kind of have to, focus on when you are comparing intermolecular forces. And the important thing to remember, though, again, is that they are additive. So, like, even though HCl experiences dipole-dipole, it still has London dispersion forces because all molecules experience London dispersion forces. And even though in general London dispersion is the weakest, if a molecule has a lot of London dispersion forces, it can be stronger than something that says has dipole-dipole attraction. All right, so let's look at this one together. So it says, in which of the following substances is hydrogen bonding likely to play an important role in determining physical properties? Methane, which is CH4, hydrazine, which is H2NNH2, methyl fluoride, which is CH3F, or hydrogen sulfide, which is H2S. So the first thing to remember is for hydrogen bonding, you need H bonded to either N, O, or F. So I can go ahead and discount anything where H is not bonded to N, O, or F. So see, in methane, it's CH4. So methane would not experience hydrogen bonding. All right, in hydrazine, we have N and H, so that's a possibility. In methyl fluoride, we do have H and F, so that's a possibility. In hydrogen sulfide, we have H and S, so that is not a possibility. So I've already narrowed it down just by getting rid of the ones that don't have N, O, or F. Hydrogen bonding doesn't occur with just any hydrogen. Now, the other part of hydrogen bonding is in one of the molecules, the H must be bonded to one of these. So in one molecule, the H will be bonded to one of these, and then it will be attracted to one of these in another molecule. What I mean by that is water experiences hydrogen bonding. Okay, so in water, the H itself is bonded to the O. Okay, so see how it's actually bonded. And then what happens, hydrogen bonding is normally drawn as kind of a dotted line. It's attracted to the O in the other molecule. So in the molecule that the H is in, it must be attached to one of these. And then it must be attracted to one of these in a different molecule. So let's look at the setup of the molecules. So in this one, we have H2NNH2. So this is kind of set up the way you would draw it. All right, so we have our two N's in the middle that are bonded, and we're going to split up our H's between them. All right, let me add up my valence real quick. So I have 2 for hydrogen, I have 5 for each nitrogen, so that's 10 plus the 2 is 12, plus 2 is 14. So once I make everybody stable, I'm allowed to have 14, 2, 4, 6, 8, 10, 12, 14. So this is what it's going to look like, not in its 3D form. Notice I did not draw it 3D yet. But you can see that the H is clearly bonded to the N, and so then if another hydrazine molecule came up, the H could attract to the N on that one. Now let's look at CH3F. So C has 4 valence electrons, H has 1 times 3, so that's 7, and fluorine has 7, which is 14 total. So my single one goes in the middle. I know F is a single one, but if you needed help with this one, I'll help you with it. All right, so I'm going to put my C in the middle, and so I have 3 H's and 1 F. Make everybody stable, 2, 4, 6, 8, 10, 12, 14. So if you notice, the H is actually bonded to the C in this one. So the H has to be bonded to the N, O, or F. So that's what discounts this one. So our answer ends up being the hydrazine, not the CH3F. So it's very important on where the hydrogen is bonded in the molecule, not just if H and then N, O, or F are somewhere in the formula. The hydrogen has to actually be bonded to one of those electronegative small elements. So, pause the video, you try this one, and then we'll look at it together. So in which of the following substances is significant hydrogen bonding possible? We have methylene chloride, which is CH2Cl2. We have phosphine, which is pH3. We have hydrogen peroxide, which is HOOH. Or acetone, which is CH3COCH3. All right, so again, we need to have hydrogen either with NO or F. So I can go ahead and discount methylene chloride because it's hydrogen with C and Cl. I can discount phosphine because it's hydrogen with P. I got to keep hydrogen peroxide as a choice because it does have O and H. I have to keep acetone as a choice because it also has O and H. Now, in hydrogen peroxide, and sometimes y'all, instead of wasting time drawing a Lewis dot structure, just use the formula to kind of help you. Okay, see how the O and the H are next to each other in this formula? That means that they are most likely bonded together. If you're not positive, you can draw it and see that they are bonded together. Acetone, see how the O is next to the C? It's not next to the H? That means in this case, it's bonded to the C. Acetone ends up looking like this, like you have a C, double bond O, and then you have a CH3 happening down here. And so again, if you wanted to sit there and draw this whole thing out, you're more than welcome to, but that's what it ends up looking like. So you can see the hydrogens are actually bonded to the C, not the O. And so they kind of show you that in the formula. So we can discount acetone. So in this case, it would be your hydrogen peroxide. Okay, so like I said, hydrogen bonding is not just about looking for these elements, it's making sure the hydrogen is actually bonded to those elements also. Alright, so the molecules of a liquid must overcome their attractive forces to separate and form a vapor when you're talking about boiling. The stronger the attractive forces are, the higher the boiling point. So boiling point and melting point are always indicators of intermolecular forces. Higher boiling points and melting points, the molecules tend to have stronger intermolecular forces. The melting points of solids also increase as the strengths of intermolecular forces increase. In general, the boiling point increases with increasing intermolecular forces, but don't forget intermolecular forces are additive. So even if we've decided something has hydrogen bonding, it still has London dispersion. Everything has London dispersion. So it says, list the substances BaCl2, H2, CO, HF, and Ne in order of increasing boiling points. Alright, so first I want to find anything nonpolar since London dispersion tend to be the weakest. So I can see that this is going to be nonpolar, the H2. I can see that Ne is nonpolar. Once I pick out the nonpolar ones, I base it off of molar mass. The lower the molar mass, the less forces, the lower the boiling point. So H2 only has a molar mass of 2 because H is 1 times 2. Ne, on the other hand, has a molar mass of about 10. I'm sorry, just kidding. It has a molar mass of about 20. It has an atomic number of 10. Alright, so now I focus on the ones that are polar and I compare polarity. Okay, so CO, that's polar, so it's going to experience dipole-dipole. HF is polar, but because it's H and F, it's actually going to experience hydrogen bonding. Okay, so we know that hydrogen bonding are very strong dipole-dipole attractions. So because CO only experiences dipole-dipole, I'm going to put it next. And because HF experiences hydrogen bonding, I'm going to put that at a higher boiling point. And then last, once you get here to BaCl2, this is a metal and a non-metal. So this is ionic, which means it's actually held together by ionic bonds. And so remember, in general, an actual bond tends to be stronger than an intermolecular force. So that's why I put my ionic one as my highest. Okay, so again, all I did was first, I just focused on the nonpolar ones, and I put them in order of molar mass. Then I focused on my polar ones, I put them in order of polarity strength. So this one's not as polar as this, and so this one only experiences dipole-dipole, whereas this also has hydrogen bonding. Then I focused on the actual bonded one, which was an ionic compound. So that's all you have to do when they ask about boiling point, is just focus on those intermolecular forces. So maybe pause the video and try this one. I'll assume you've done that and we'll look at it together. So it says identify the intermolecular attractions present in the following substances. So we have CH3CH3, CH3OH, and CH3CH2OH. So the first thing I notice immediately is I can tell this one has hydrogen bonding and this one has hydrogen bonding. And I can see this one clearly does not have hydrogen bonding. So we're putting it, we're identifying what intermolecular attractions are present. So I can see this one does not have hydrogen bonding. It would actually barely even have any dipole-dipole attractions because of the shape of the molecule. So for CH3, I would just put London dispersion. Okay, if it had any dipole-dipole attractions, they would be so weak that it wouldn't make any difference. So I would mainly put London dispersion for that because the dipoles, even the weak dipoles it would have, would cancel out anyway due to its shape. All right, so now I have two that have hydrogen bonding, but remember, they are additive. So if it has hydrogen bonding, I'm just going to circle that because that would be, of course, the most important one. It still technically has London dispersion because all molecules have London dispersion. And then technically it has dipole-dipole attractions too. Okay, but hydrogen bonding would just be the most important of those. And then our last one too, CH3, CH2OH, would again have hydrogen bonding because of that OH, but it would still have London dispersion and dipole-dipole because they're additive. And then it says which substance has the highest boiling point. Well, these two have the most intermolecular forces, so clearly I can go ahead and discount CH3, CH3. However, these have the same intermolecular forces, so now I'd have to compare and see who has more. Well, this molecule is going to have a larger molar mass than this one, because see how it has the extra CH2? So since it has the higher molar mass and technically a longer chain of carbons, this one just has the one, this one has two, it's going to have more London dispersion forces than the other one. So hopefully you got that right. All right. So next thing we're going to talk about is cohesive and adhesive forces. So intermolecular forces that bind similar molecules together, such as hydrogen bonding and water, are called cohesive forces. Intermolecular forces that bind a substance to a surface are called adhesive forces. So when molecules of a substance attract one another, it's called cohesive. And then when they attract to a surface of some type, we're going to talk about glass in a second, that's called adhesive because they're adhering to the surface. So that's why a meniscus forms. And so the picture may be hard for you to see on the video, but in water, if you put that in a test tube, it'll form a meniscus that curves downward. But mercury, on the other hand, actually forms a meniscus that goes upward, which is awkward because we're used to seeing the meniscus form downward. So let's talk about what's happening. So the meniscus of water is U-shaped because the adhesive forces between the water and the glass are stronger than the cohesive forces of the water. So the water wants to adhere to the glass, so it kind of climbs up the sides of the glass. That's what causes it to have that U shape. Whereas mercury does the exact opposite. It's kind of like running away from the glass. So the meniscus of mercury curves downward because the cohesive forces, the forces that hold the mercury atoms together, are greater than the adhesive forces between the mercury and the glass. So you can tell based on the direction of the meniscus which forces are stronger. So these forces are also what allow capillary action to happen. So the rise of liquids up very narrow tubes is called capillary action. So if you ever had a straw in water, especially a really thin one, sometimes you'll see like the water level in the straw slightly higher than the rest of the liquid. Again, it needs to be a thin tube. And so what that means is the water is more attracted to the glass. So again, it's like climbing up the glass to adhere to it. So those adhesive forces are responsible for capillary action. Now, when you're comparing intermolecular forces, it's very important to note when something is a network solid because they are going to trump all the intermolecular forces in strength. So a network solid is just a solid in which every atom is covalently bonded to every other one. Network solids are extremely strong and have a high melting point. And so the two that you really need to know are diamond and SiO2. So if you're putting things in order of boiling point and diamond or SiO2 is on there, those always have the highest, because in order to melt or boil them, you are breaking covalent bonds. You are not breaking intermolecular forces. You are breaking strong covalent bonds. So diamond and SiO2 will always be at the top of the boiling point or melting point list for those. All right, so let's knock out our section assessment. So how do electronegativity values determine the charge distribution in a polar covalent bond? Well, remember, for polarity, we assign a partial positive and a partial negative. The partial positive is the lower number, and the partial negative is the higher number. And by number, I mean the numbers from the electronegativity chart. Number 2, what happens when polar molecules are between oppositely charged plates? Well, this is what happens. Let's say we have our plates, and one's positive and one's negative, and let's say we have an HCl molecule on the inside. Well, H has a 2.1 electronegativity, Cl has a 3.16, so H would be partially positive and Cl would be partially negative. So if I put this in between the plates, the positive H would attract to the negative plate, and the negative Cl would attract to the positive plate, so they would line up in this orientation. All right, number 3, compare the strengths of intermolecular attractions to the strengths of ionic and covalent bonds. Well, remember, bonds tends to be stronger than intermolecular attractions. Okay, however, London dispersion tends to be the weakest of the attractions, then dipole-dipole, then hydrogen bonding, and then your bonds tend to be stronger than all of them. Now, of course, there are exceptions. That's why I always say in general and tends to be. But in general, the bonds are going to be stronger than all the intermolecular forces. So number 4, it says not every molecule with polar bonds is polar. Use CO2 as an example. Well, first we have to draw it. So C has 4 valence electrons, O has 6 times 2, which is 12 plus 4, which is 16. If you're not good at Lewis dot structure yet, go back to the 8.2 videos, because I'm not going to slow down on that anymore. All right, so to make everybody stable, all right, I'm allowed to have 16, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I need 2 more bonds. I'm going to put one on both sides. I then adjust for my octet rule. So now I have 2, 4, 6, 8, 10, 12, 14, 16. So see how once you get good at Lewis dot structure, it's super fast. All right, so C has an electronegativity of 2.55. O has an electronegativity of 3.44. That means my dipoles are going to point towards my O's. So since they're in opposite directions, because this is a linear molecule, it's not bent, they cancel out. So the dipoles cancel. That's where the shape becomes incredibly important, because if this had been a bent molecule, they wouldn't cancel, and then overall that molecule would be polar. Alright. So last one, it says draw the Lewis dot structure for each molecule, identify the partial positive and partial negative atoms of each molecule. So again, I'm going to draw the Lewis dot structures incredibly quickly because you should have learned how to do that in 8.2. I am not going to focus on shape because it's just having me label partial positive and partial negative. So H has 1 valence, O has 6, O has 6, H has 1 for a total of 14. The order it's in is the order that it bonds in. I go back and make everybody stable. I'm allowed 14, 2, 4, 6, 8, 10, 12, 14. So if you look at your electronegativity chart, H has 2.1 electronegativity, O has 3.44. Remember, the higher the number, the partial negative charge goes with that. And then the lower number gets the partial positive. Alright, so next we have BrCl. So Br has 7, Cl has 7 for a total of 14 valence electrons. So since it's just 2 atoms, this is my only option for bonding. I make everybody stable. I'm allowed 14, 2, 4, 6, 8, 10, 12, 14. Apparently our bell's ringing. So now I'll look at my electronegativity chart. chart. So Br is 2.96, Cl is 3.16. So since Cl has the larger electronegativity, it is the partial negative atom. All right, next is HBr. Oh, well, let me add up first. So 1 for H, 7 for Br, for a total of 8. So I bond them, make everybody stable. Remember, H only follows duet rule, it only needs 2. So I'm allowed 8, 2, 4, 6, 8. And then I look at my electronegativity chart. So H has 2.1, Br has 2.96. So since Br has the larger electronegativity, it gets the partial negative. And then the last one, we have H2O. Hopefully at this point you've just memorized what H2O looks like, but if you haven't, just do that because it's going to be there a lot. Now, we know it's a bent molecule. I'm just going to draw it, well, I'll just go ahead and draw it bent because it is. So H2, so I'm going to do 1 times 2 for hydrogen and 6 for oxygen. So that gives me 8 valence electrons to work with. I'm going to kind of move over here so you can see it better. So I'm going to put my oxygen, my 2 hydrogens, make everybody stable. I'm allowed 8, 2, 4, 6, 8. And then this one is obviously incredibly similar to part A. H is 2.1 and O is 3.44. So my O would be partially negative and my H's would be partially positive. All right, so the important thing is if you don't have an electronegativities chart, get an electronegativities chart. If you're not good at Lewis dot structure, go back and watch the 8.2 videos because you need to get good and fast at it. You don't have time on a test to answer a question like this and take 15 minutes to draw this structure. So you got to get fast and good at it. So if you're not good at it yet, then go back to 8.2.